The next topic we're going to talk about is nuclear chemistry, and I apologize, I don't have a very good voice right now. So, as we've done before, we're going to start with some simple definitions. The first is that of radiation. These are small particles or just pure energy with very high energy. So, obviously, things that have pure energy are pretty high in energy as well. But these are caused by a breakdown of unstable isotopes. So, that means that we've got elements of chemicals with neutrons in some type of unstable form. So a radioisotope is one that's unstable. So that's the sort of circle that goes around here. We say that they emit radiation spontaneously. Now, be careful with that word. It doesn't mean that it happens instantly. It doesn't mean that it happens right now. It just is happening constantly. Okay. Most of the time we see that large atoms are radioactive due to their instability because they just get too big. So an example of these, 35 chlorine and 37 chlorine are stable as isotopes, but if you have a 36 chlorine, they hardly exist for long because it's radioactive. They all have the same number of protons, and the electrons we don't even consider here. So keep in mind that when we say 37, the 37 with the 17 protons is assumed. So radiation is a very broad term. There's different types of radiation. So let's talk about what those types are, okay? The first is that of an alpha particle. So alpha particles are abbreviated with this alpha, or they can be seen as a 4-2 helium because they have a mass of 4 and a charge of 2, but there's no electrons here, so be careful there. But that's what an alpha particle is. So if you remember, we talked about Rutherford's experiment. He was shooting alpha particles. This is what he was aiming at the gold foil. This is what happens when a nucleus ejects 2 protons and 2 neutrons from its center. Next, we have a beta particle, and this looks like a beta or 0 with a -1 at the bottom E. This is a very high energy electron that has a charge of -1 and no mass. So this is a result of a neutron splitting into a proton and an electron. So that can happen. So a neutron can basically give its mass and its positive, like split itself into a positive and negative. Its mass and its positive charge goes to make a proton that stays in the nucleus, and it ejects a negatively charged electron. The atom loses a neutron and gains a proton in this case. Okay. Now, the opposite of a beta particle is something called a positron. These don't happen very much. This would be a beta plus or an E with a +1 charge at the bottom. This is antimatter. That means that when this is the opposite of real matter, yes. That means that if this hits a real electron, they cancel out to make nothingness, and that's when really large amounts of energy go. But you're negating mass, so that's like, we don't want to destroy the universe. This is relatively rare, which is a really good thing. So here, an unstable proton splits into a neutron and a positron, okay? So the neutron stays in the atom, and the atom loses a proton and gains a neutron. Next, we have what's known as a gamma ray. These are like the little Y type of symbol, and sometimes you'll see them with 0 above and below. This is just sheer energy, high energy. Gamma rays are part of the electromagnetic spectrum, and there's no particle that really comes out here. Others can include, you can have an actual ejection of a proton. So if you see something like that, or P, that is a proton. Or you can have an ejection of a neutron, which would be represented in this form or that. So when radiation hits the body, this is not good for your body. It mostly affects cells that are in rapid division. So this includes reproductive organs, bone marrow, skin and hair, digestive tissue, blood cells, because that's made in the bone marrow. Children can be highly affected by radiation. Radiation affects cancer that are rapidly dividing, and that's the reason why radiation is used to cure cancer. But be aware that radiation can cure cancer, but it can also cause cancer. There's a little conundrum when it comes to cancer radiation, or radiation for cancer use. Anytime that you or anybody you know is working with radiation or with patients who are undergoing radiation, you need to make sure that you're using proper shielding and distance. Distance is one of the best things that you can do to protect yourself. There's different things that stop different types of particles. Basically, the bigger those particles are, the more easily they are to be stopped. So alpha particles can be stopped very easily by clothing. Beta particles take heavy clothing that's higher energy. Gamma particles, this will pass through you entirely. It takes lead or heavy concrete to be stopped. So take this seriously. If you happen to work in this field or are going to work in this field, stay away from as much as possible. So next we need to talk about the different type of equations that can be used. So these are all examples of different types of decay. Decay, we mean by decay that one thing is splitting into two other things. So you're decaying because you're losing something from the original atom. So here we have 240 over 94 plutonium. This will decay into uranium-236, and we have an alpha particle here that comes out. Now note that we have 236, if you add that to 4, that will get you to this 240. And if we add 92 and 2 together, that will get us to 94. That's how we balance these equations, you all. It's pretty simple. You have to have the same number up top on one side equal the same number up top on the other, and same thing for the one that's below, okay? Keep in mind that this little arrow sign in chemistry is kind of like an equal sign in math. It's just showing that this is the before and this is the after. So this was what we refer to as the reactants, and this is what we refer to as the products. Okay. Next we have beta decay equations. Beta decay is the result of a neutron splitting into an electron and proton. So the proton count, or the atomic number, will increase by 1. Sorry about that. So what that means, though, is that if we start with carbon 14, we end up still with 14 on the top in our nitrogen, because this guy has 0 mass. But down below, we can see that we started with 6 protons, but we end with 7 protons and a -1 charge from that electron. So if we add together 7 and -1, that still equals 6. And so this is a balanced equation, and we're good to go. Positron decay equations might be a little bit more difficult, but not really. It's the same concept. One proton changes into a neutron plus an anti-electron. So here, if we start with carbon 10, we end up getting boron with the same mass of 10. But now our carbon 6 has been changed to boron because our atomic number changes, and we have a +1 charge on that positron. I think that gamma decay is the easiest one to see because you start with something that is noted as being metastable. Basically, it shows you a big M right there. And what that tells you is that this is not a very stable type of arrangement for that particular atom. And so gamma radiation comes off of that, and you're just left with a 99, in this case, technetium. So the energy is just rearranged. Unstable elements can come from many different sources. Some of them are occurring naturally, and we can also make some man-made. And what we do to make man-made radioactive elements is that we do something called forcing, which is basically where an atom is bombarded with other types of particles. So one example of that could be here. We've got 27 aluminum. If we bombard that aluminum with a neutron, we can end up with 28 aluminum. Make sure that the top numbers add up when you're balancing these, either whether it be on the right hand side or the left hand side because you're doing a bombardment, and make sure that the bottom numbers also still add up when you're balancing these. So you also know measuring radiation is usually in a Curie or a becquerel, at least in the scientific world. But when it comes to medicine, we use RADS, which stands for radiation absorbed dose, or REMS, which is radiation equivalent in humans. So those types of terms are also used. Radiation sickness is a result of too much exposure. You can't undo exposure period, but you can mitigate some of the symptoms and deal with that in different ways. This is a very serious illness that you don't want to have, so again, protect yourself. Thank you very much.